Hello my scholars, you are welcome to my school YouTube channel and my name is Frank. In today's video we shall be discussing about magnetic field. So relax, do not go anywhere, I'll be right back. You are welcome back to my school YouTube channel. Like I said, we shall be discussing about magnetic field in this video lesson. So before we begin with our lesson, let's quickly run through the objective for today's video lesson. Objective number 1, plot the magnetic field around I, a bar magnet, II, a straight line carrying current, III, a solenoid. Then 2, locate the Earth's magnetic north/south direction. Then 3, explain the magnetic force on a moving charge. Then the fourth one, state the relation between magnetic force and the motion of a charge in a magnetic field. So let's kick off with the lesson proper. So here, simply we are just going to be introducing the concept of magnetic field. But remember, when we were discussing about description of field, we made mention of magnetic field. Okay, in today's video, we are going to be treating magnetic field proper. So let's begin by defining magnetic field. So a magnetic field is a region in space where a magnetic force is exerted or felt. Okay, magnetic field is a vector field. Okay, meaning that it has direction and it also has magnitude. So the direction of a magnetic field is taken as the direction of the force on a north pole if placed in the field. Now let's talk about the patterns of magnetic field. So we are going to be talking about the patterns of magnetic field around the bar magnet, around unknown poles of bar magnet, and also that of like poles and others. Okay, so let's begin with I. So for I, the diagram here represents the pattern of magnetic field around a bar magnet. So as you can see on the diagram, the magnetic lines of force, okay, emanates or begins from the north pole and then ends in the south pole. Then the same thing for unlike poles, okay, so this is the north pole and this is the south pole. So the magnetic field also starts from the north pole, okay, and ends in the south pole. Okay, then we also have for like poles, when the two poles are the same, that is, you can have north-north or you can have south-south. So in between them, you see a point marked X. Okay, so that point marked S is referred to as the neutral point. So this point, the net magnetic force is 0. So just take note of that. So let's move to the next slide. So on the next slide here, we are going to be talking about the pattern of magnetic field around two bar magnets placed near each other side by side. So these are the two bar magnets. So this is when for the first bar magnet you have north, and for the second one you also have north. Then the other side you have south and south. Then this is a case where you have north, okay, opposite south, and you also have south opposite north. Okay, so you also see the point marked S. So that point marked S is referred to as the neutral point, and like I said earlier, that point, the net magnetic field is 0. Okay, so now let's discuss about the pattern of magnetic field around a straight conductor carrying current. Okay, so this is the diagram of the whole setup. So here we have a cardboard paper, then here we have iron filings. Then here we have a conductor, or a conductor carrying current, or a wire carrying current, or a current carrying wire. Okay, so here we have the key, more or less like the switch. Then we have the resistor. Then we have the source of the energy. Okay, so let's move to the next slide to describe what is on this diagram. So number 1, pass a straight wire. Of course, the wire is copper wire, vertically through a hole on the cardboard sheet head horizontally. Then 2, connect the ends of the wire to the source E of electricity as shown above in the diagram that we have seen in the previous slide. With the key open, spread iron filings on the board and gently tap the board. No pattern is formed. Then close the key and again tap the cardboard gently. It will be observed that the iron filings arrange themselves in series of concentric circles about the wire as center. So when we talk about concentric circles, we are talking about circles of different sizes, but they have common center. Okay, so in this case, the center of the concentric circle is the wire. Okay, this shows that there is magnetic field around a straight conductor carrying current. The pattern of the field consists of concentric circles with the wire as center. The direction of the field depends on the direction of flow of the current. Such direction is known by applying the right hand grip rule, okay, also known as the clenched fist rule. So let's move to the next slide to state this rule. So the right hand grip rule or the clenched fist rule states that if the straight wire is grasped with the right hand so that the thumb points in the direction of the current, then the direction in which the fingers are coiled indicate the direction of the magnetic field. So as you can see in this diagram, this is a straight wire and this is the hand that grabs the wire, okay, just like this, but with the right hand. So this hand, the thumb here, okay, shows or indicates the direction of the current, while the fingers here indicates the direction of the magnetic field. Okay, so there's another law again, or there's another rule again called the Maxwell corkscrew, which also shows the direction of current, okay, in a conductor carrying current. This rule states that if a right-handed corkscrew is turned so that its tip travels along the direction of current, the direction of rotation of the corkscrew gives the direction of the magnetic field. So let's move to the next slide. This is the rule, the Maxwell corkscrew rule, okay, depicted in diagram. So this is the corkscrew, okay, and this is the direction of the magnetic field, and this is the direction of the current. While here represent the direction of rotation of the corkscrew. So let's talk about magnetic field around a solenoid. So a solenoid is a long cylindrical coil of wire whose turns are wound close together. Okay, it is a long cylindrical coil of cylindrical coil of wire whose turns are wound close together. Okay, so when a current is passed along the turns of the solenoid, a magnetic field is created inside and around the solenoid. The field pattern is similar to that of a bar magnet. The lines of force emerges from one end of the solenoid and returns through the other end. The end from which the lines of force emerge behaves like a north pole, represented by letter N, while the end by which they return behaves like a south pole, represented by letter S. So let's move to the next slide. So this is the diagram of a solenoid, okay? So now let's talk about magnetic and non-magnetic substances. Okay, so what are magnetic substances? So magnetic substances are materials that can be magnetized, okay? Or we can especially say they are substances which can attract or can be attracted even by a weak magnet. An example of such materials are iron, steel, cobalt, nickel, and manganese. Okay, they are also called ferromagnetic substances. So you can refer to magnetic substances as ferromagnetic substances. So on the other hand, we have non-magnetic substances. So non-magnetic substances are those substances that are not attracted by magnet. Okay, they cannot be magnetized. An example of such substances are copper, brass, wood, glass, plastic, etc. Okay, so these substances cannot be magnetized. They cannot be turned into magnets. So let's move to the next slide. So on the next slide, we are going to be discussing tests for magnets, magnetic substances, and non-magnetic substances. Just a way to show if a substance is a magnet or not. Okay, so when a substance is freely suspended from its center of gravity by means of a thread, if it settles in a north-south direction, then that substance is a magnet. This is very important, okay? So when a substance is freely suspended from its center of gravity by means of a thread, and that substance settles in a north-south direction, then just know that that substance is a magnet, okay? Then a magnetic substance will be attracted by a magnet. So any material that is attracted by a magnet, you just know that that material is a magnetic substance. But the one that is not attracted by a magnet, just know that that substance is a non-magnetic substance. Now let's move on to talk about temporary and permanent magnets. Okay, so temporary magnets are those magnets which loses their magnetic properties easily. Okay, they are made from soft iron. They produce a strong magnetism, but for a short time. They are applied where strong magnetism is required for a short time, such as in electromagnets. Let's move to the next slide. Now, a permanent magnet are those which do not lose their magnetic properties easily, and they are made from steel. They produce a relatively less strong magnetism. They are applied where magnetism is to be sustained for a long time, and a good example is the compass needle. So let's talk about magnetization. So magnetization is just a process of making a magnet, okay? So magnetization is a process whereby a magnetic substance is made to gain magnetism, thereby turning it into a magnet. Or simply put, magnetization is the process of making magnets. So we have different processes of making magnets, and we are going to be discussing this process these processes one after the other. So let's begin with the first process, which is the electrical method. Okay, so here the material to be magnetized is inserted into a solenoid having the ends of the coils connected to circuit. So then the current is switched on for a few seconds and then switched off. When tested, the specimen, okay, so the specimen here represents the material to be turned into magnets, okay? So when tested, the specimen is found to have been magnetized, okay? But remember that here, you actually place the specimen in the north-south direction, okay? When you are trying to turn that specimen into a magnet. So let's move to the next slide to discuss about other methods. Okay, so for the polarity of the magnet, okay, that is made using the electrical method, if the direction of current viewed from one end is clockwise, then that end is the south pole. If the direction of current viewed from the other end is anti-clockwise, then just know that that end is the north pole, as you can see in the diagram below. Okay, so if the direction of current is from this side, is clockwise, okay, from this side, just know that it is the south pole. But if it is anti-clockwise on the other side, that is the direction of current is anti-clockwise on the other side, just know that it is the north pole. Okay, now let's talk about the second method, which is the contact method. Okay, so for this contact method, it is divided into two. We have the single touch method, then we have the double touch or the divided method. Okay, so let's discuss the single touch method. So this is the diagram of the single touch method. We have a bar magnet that is inclined at a certain angle. Then this is the specimen that you actually want to turn into magnet. So initially we don't know whether if here is the north or here is the south pole. Okay, so on the next slide we are going to discuss how this part, okay, came to become the north pole and here became the south pole. Okay, so the magnet is kept in an inclined position, okay, as shown, and dragged along the specimen from end A to end B and lifted well away from the specimen and brought again to A in the same inclined position as we can see in the diagram in the previous slide. So the process is repeated several times, right? So it is observed that after the stroking process, that the specimen has become magnetized. So the end A will have the same polarity as that of the pole of the magnet used for stroking. Let's return back to the previous slide. Okay, so that is why this end is the north pole. Why? Because this is the end of the pole of the magnet that was used to strike this end. So after the whole stroking process, okay, since this end of the pole of the magnet is north, so this end that was struck, okay, will also become the north pole of the specimen, while the other end will become the south pole. Okay, so let's return back. Now, let's talk about the double or divided touch method. So the double divided touch method is almost similar, okay, but the difference is that the stroking takes place at the middle of the specimen and the specimen is stroked with two poles of magnet. So this is one and this is another one. So at the end of the stroking, if this side was stroked with the north pole, okay, on the specimen, then it will become the south, while this other side will become the north, since it is stroked with the south pole of a bar magnet. So let's move to the next slide to really discuss about the process. So 2 bar magnets are held in inclined position with opposite poles touching the magnet at its middle as shown in the diagram that we just saw. Okay, so the specimen is stroked simultaneously outward from its center in opposite direction by the opposite poles of the magnets, and at the end of the specimen the magnets are lifted well away from the specimen and brought again to the center of the specimen in the same inclined position. The stroking is done repeatedly for some time. It is observed after the stroking process that the specimen has been magnetized. Now take note of this. Each end of the specimen will be found to have an opposite polarity to that of the pole stroking in its direction. So the divided touch method or the double touch method provides a stronger magnet in shorter period than the single touch method. So let's move to the next slide. So on the next slide here, we are going to be discussing about demagnetization, which is the opposite of magnetization. So demagnetization is a process whereby a magnet is made to lose its magnetism. Okay, and we also have different methods of doing that. So the methods of magnetization are electrical method, then we also have mechanical method, then we also have the heating method. So let's begin with the electrical method. So the electrical method is more or less like the opposite of when you are making a magnet. The only difference is in the direction in which the specimen is placed in the solenoid. Okay, so for the magnetization, if we are using the electrical method, the magnet, okay, is placed in the solenoid with its axis pointing in the east-west direction. But when we are making a magnet, it is the axis of that specimen that we want to turn into a magnet is placed in the north-south direction. Just take note of the difference between the two processes. Okay. Now pass an alternating current through the solenoid for a few seconds and then slowly withdraw the magnet to a long distance away. The rapid reversal in direction of the alternating current causes the polarity of the magnet to reverse several times in 1 second. This process causes the magnet to lose its magnetism, that is, to become magnetized. Now take note of this, that the electrical method is the most effective way of demagnetization. So sometimes you can be asked in an exam. Okay, so just take note of it, that the electrical method is the most effective way of demagnetization. So let's talk about the mechanical method. So the mechanical method simply involves the use of hammer to hit the magnet hard when it is pointing in the northwest direction. And after the hitting, it will be found to have lost its magnetism. Let's move to the next slide to talk about the last method of demagnetization, which is the heating method. So in this method, the magnet is strongly heated and it will be found to have lost its magnetism after the heating process. Okay, so now let's compare the magnetic properties of soft iron and steel. Okay, so on my left hand I have the iron and on my right hand I have the steel. Okay, so one, the soft iron is more easily magnetized, while the steel is more difficult to magnetize. Okay, so that is the first point. Then two, the soft iron produces stronger magnets, while the steel produces weaker magnet. Of course, we've also touched all these ones in previous slide. Then number three, the soft iron loses its magnetism more quickly, while the steel retains, or better still, loses its magnetism more slowly. Then the last but not the least, the soft iron is used for making temporary magnets, while the steel is used for making permanent magnet. So this is where we bring the preview of today's video on magnetic field to a close. I believe you enjoyed the video, but then you can enjoy the complete video by simply clicking on the link in the description below, and that will take you to my school website. There you will have to subscribe to enjoy the complete video. So in the complete video, you shall learn about magnetic field of the earth. You shall also learn about magnetic elements of a place. Okay, that is the elements that determines the magnetic field of that place. Okay, and many more. So I believe you enjoyed this video. If yes, please do not forget to hit the like button, click on the subscribe button, and lastly, tap on the notification bell to get informed as soon as we release the next videos.